You will come across finding the limits of functions that have absolute values in them. So I need to give you a quick warning about absolute value functions. They are really piecewise functions in disguise. Absolute value functions are just really common piecewise functions, so they have this special notation to make them easier to work with. I'm going to change this notation back to piecewise function notation. So here we have f of x equals, you don't have to be able to do this, but just in case you're curious, all I did was rewrite exactly what I see here with the absolute value with a set of parentheses where the absolute value used to be. Now there's those parentheses, and then in front of the parentheses you put a positive and a negative. And now I'm going to simplify that. So negative x minus 4 minus 2, simplify. So when I simplify these, I'm going to end up with this. And then I'm only going to use the equation y equals negative x minus 6 when x is less than or equal to negative 4, and the y equals x plus 2 when x is greater than negative 4. The reason I knew it was negative 4 is because whatever number makes what's inside of the absolute values equal to 0, that is where the sharp spot on this absolute value is going to be. So that's kind of our changing point there. All right, so might as well review a little bit of graphing piecewise functions. So graph y equals negative x minus 6, but we're only going to use the piece where the x's are less than or equal to negative 4. So we're going to leave that piece off. Right, here's negative 4, and we're only going to use the piece to the left of negative 4. Then y equals x plus 2 is that line, but we're only going to keep where the x's are greater than negative 4. So we'll leave that one off. And then if we take these two pieces together, we are right back to where we started. I'm hoping in showing you that absolute value functions are really piecewise functions, that when you see a function has an absolute value in it, that you might stop and think for a moment and think, oh, there might be a little more to this problem. And there is sometimes. So let's see when there is and when there isn't an issue. If we're finding the limit algebraically of an absolute value function, that's a pretty basic one. It really won't be much different. I substitute in 2 because step 1 in the algebraic process is to plug and chug. And then when I simplify, I end up getting 4. And the answer here is 4. We should always feel good when we substitute a number into the function and we get out a real number value. Looking at these two limits, let's kind of look to the right there and see what does y equals the absolute value of x minus 6 over x minus 6 look like? Well, here you can definitely see that it's a piecewise function. To the left of 6, we have a horizontal line at negative 1, and to the right of 6, I have a horizontal line at positive 1. All right, we'll go ahead and start the process. Plug and chug. I substitute in 2, and I end up getting negative 1. That's great. That works out just fine. The reason why this is working out is because not only because we just got a real number solution, but the number that we're getting close to does not make that absolute value equal to 0. If the number you're getting close to makes the absolute value equal to 0, you likely have a break there. So here we're fine because we got out the answer negative 1, we're good. But how about if I substitute in 6? When I substitute in 6, I get 0 over 0, and we know that's inconclusive. It doesn't mean that guaranteed that it is the limit exists or it doesn't exist. We would want to factor, cancel, resubstitute. But you cannot cancel absolute value of x minus 6 with plain x minus 6. So since you cannot cancel that, you have to know your functions. That's why we spend a lot of time in pre-calc studying functions. If you don't know at least you see an absolute value in the function and you take pause because you got 0 over 0. And I'm hoping you know that right now you cannot cancel an absolute value with something that's not an absolute value. So you could kind of fall back a little bit on that table just to check a bit, pick a couple numbers close to 6 from the right. And when you do pick numbers close to 6 from the right, you'll start getting out positive 1. And you pick a couple of numbers close to 6 from the left, and you're going to start getting the answer negative 1. We are not heading to the same answer. This would be a reminder that, oh, yeah, at 6, absolute value, there's a break there. So the limit here does not exist. In summary, using the algebraic method, you start by substituting the number into the function, and if you get out a real number solution, like 10 or 0, then that's your answer. If you get a number divided by 0, then the answer to the limit is does not exist. If you substitute the number into the function following step 1, and you get 0 over 0, then you've got more work to do. You want to try to factor, cancel, and then resubstitute. Here, we were able to do that. If you have followed step 1 and you got 0 over 0, you tried to factor and you just couldn't, well then next, the third step is to multiply the numerator and denominator by the conjugate. Only multiply your numerators together. Something will now cancel, so you can resubstitute, simplify, and you've got your answer. When using the algebraic method, if you see an absolute value in the function, then you need to take it a little slower. You still are going to substitute the number into the function and see if you get out an answer. If you get out a real number, then that is your answer. But be especially careful if the number that you're getting close to makes inside the absolute value equal to 0, because there might be a break there. There likely is.